Okay, today we are going to begin looking at estimating a population mean, that is constructing confidence intervals for the population mean, for mu, ladies and gentlemen. So in this section, we'll be creating and interpreting confidence intervals. We'll be determining sample sizes. We're going to look at how the margin of error changes with the sample size and level of confidence. And we're going to determine sample statistics from a confidence interval. So, back in the first section, 8.1, when we first introduced this notion of a confidence interval, we estimated a mystery mean for mu by constructing a confidence interval with a sample mean of 240.79. You can look back at those notes if you need to. So remember, to calculate our 95% confidence interval for mu, we're using this formula. We saw it in 8.1. We saw it when we were estimating our proportions. And now we are going to use it for mu yet again. So we have x bar plus or minus z star, our critical value, times our standard deviation, times sigma over square root of n. So there we have it. We calculate our margin of error, which is 9.8, so 240.79 plus or minus, that gives us this interval. So when we're choosing a simple random sample from a population having an unknown mean and a known standard deviation sigma, as long as the normal and independent conditions are met, that is the 10% condition for independence and the normal condition, meaning either the population's normal or n is greater than or equal to 30, then we have our formula for the confidence interval right here. Our z star, our critical value, comes directly from our normal distribution. The margin of error. When choosing the sample size, our margin of error will determine how big of the sample we need is. So margin of error, ME, is our critical value times sigma over root n. We determine the sample size the same way we did with the proportions. To determine the sample size that will yield a confidence level C for a population mean with a specified margin of error, we do the following. We get a reasonable value for the population standard deviation from an earlier or a pilot study, a similar study. And once we have that, we find our critical value, z star, from a standard normal curve for confidence level C. So whatever our confidence level is, that determines our critical value. And we can use these, we can solve this equation for n to get our sample size. So here's an example. How many monkeys do we want? So researchers would like to estimate the mean cholesterol level of a particular variety of monkeys that is often used in lab experiments. They'd like their estimate to be within 1 milligram per deciliter. So this is our margin of error. We want to be within that much of the true value of mu at a 95% confidence level. It so happens that there's a previous study that was done with this variety of monkey that suggests that the standard deviation is approximately 5 milligrams per deciliter. So our critical value for 95% is 1.96. Our standard deviation that we're going to use is 5. We know that from our previous study. And we want this to be less than or equal to 1. Our margin of error is 1 milligram per deciliter. So now we solve for n. We multiply both sides by square root of n. And then we divide both sides by 1. If this wouldn't have been 1, if this would have been 7, we would divide both sides by 7 here. And then we square both sides. And we get that n has to be greater than or equal to 96.04. So if we sample 97 monkeys, we should ensure that our margin of error is no more than 1 milligram per deciliter at a 95% confidence level. Now, what if we don't know the population standard deviation? Do you think that could ever happen? And I hope you're saying, yeah, that could happen. How are we supposed to know that? Well, sometimes we don't. A lot of times we don't. So when we're sampling when we have a sampling distribution of x bar that is close to normal, We can find probabilities involving x bar by standardizing, finding the z-score. This is our formula for a sampling distribution. We've seen this. And what we get is a mu of 0 and a standard deviation of 1 when we do the standard normal distribution. When we don't know sigma, we can estimate it using the sample standard deviation S sub x. So we're taking the standard deviation of our sample. Now, we use the sample proportion, our p hat, to calculate standard deviation in the previous section. But what happens when we standardize this? What happens when we use S sub x as our estimate for sigma? Well, what happens is our new statistic isn't normally distributed anymore, guys. And that creates a whole different ball game for us to play with. We are no longer going to be able to use z-scores because z-scores are for normal distributions. If we don't know sigma, we can't use a z-score as our critical value. We have to use something called a t-score. T as in tiger. When we standardize based on the sample standard deviation, that is when we don't know sigma, the population standard deviation, our statistic will follow a t distribution. In some texts and some statistics class, this is called a student t distribution. It has a different shape than the normal curve, slightly different. It's symmetric with a single peak at 0. That's sort of the same. However, it has much more area in the tails. Here is our t distribution. Here is our normal distribution. Notice the symmetry. Notice the peak is still in the middle, but there's a lot more out here on the fringes, out to the tail ends of this distribution. Just like a z-score, t will tell us how far x bar is, each x bar, is from its mean in standard deviation units. So when we say t is 1, we mean that our sample statistic, our x bar, is on average it's 1 sample standard deviation away from the mean. Slightly different than population standard deviation, ladies and gentlemen. It's a difference in the number that we're using in the calculation. And because of that number, the shape is different. There is a different t distribution for each sample size. So the sample size determines the distribution. And its degrees of freedom is how we specify and label these different t distributions. The degrees of freedom, df, is n minus 1. So if we have a sample size of 10, the degrees of freedom would be 9. We're not going to get into why this changes it. We're not going to get into the calculation of how this works. But just know that as the sample size changes, so does our t distribution. And we look up the degrees of freedom as being 1 less than the sample size. So our t-score, our t distribution, with degrees of freedom of n minus 1, we find using this formula. So we're going to calculate some of these in just a moment, but let's look at some facts. As we change our degrees of freedom, so the dashed one is 2 degrees of freedom, the blue one is 9 degrees of freedom, the purple one is our standard normal distribution. They're similar in shape, but the spread is different. We get more stuff out here in the tails. The spread of the t distributions is bigger than the standard normal distribution. And as the degrees of freedom increase, our t distribution approaches the standard normal curve even closer. So as n gets bigger, we get closer to our standard normal distribution, our nice bell curve that we use z-scores with. The t-distributions have more probability in the tails and less in the center. It's more spread out. There's more variation. So we don't use table A. We use table B in the back of the book in our formula packet to determine our critical values, t star, for t-distributions with different degrees of freedom. So let's do one of these. Let's find ourselves our first t value. Suppose we want to construct a 95% confidence interval for the mean of a normal population based on a simple random sample of size 12. What critical t-score should you use? Well, they don't tell us the standard deviation, do they? We know we need to use t. So we're going to look at the table in the back. And in table B, we're going to consult the row corresponding to the number of degrees of freedom. We have a sample size of 12. That means the degrees of freedom are 11. So we're looking in this row. What's our confidence level? Our confidence level is 95% here. The top, this is the upper tail probability. This is how much is in each one of the tails on either side of our normal curve. So each tail has 0.025% in it, or 2.5%, I should say. Our t-score is where these two values overlap. 11 degrees of freedom, 95% confidence. Our t-score, our critical value, is 2.201. And this is where I shall leave off for today. We'll get into actually constructing these confidence intervals in part 2.